bounce, 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 bounce. Okay, what we're going to look at here is a C3 problem for Unit 11. So Unit 11, C3. What we're going to look at here is a combination of moments of inertia torque, and angular accelerations, and how we can put all of those together. So let's pretend for a second that we go back in time to my early childhood, you know, the late 1800s, where all young Coach Botzer was playing with was a wooden hoop and a stick that pushed it. Okay, so I've got this wooden hoop and this stick that's pushing on the hoop, and with it I can, you know, gingerly push around the hoop and have a splendid day. You know, just standard things that I did as a child. Give an idea of what these hoops were like. These hoops were about the size of a hula hoop, so they had a radius of about 0.75 meters. I mean, all of them were slightly different, but you know, this one could have a radius of 0.75 meters. They were fairly large. And as a small child, I wasn't that strong with my, you know, hoop and stick, but I could probably easily push the stick with a force of something along the lines of 12 newtons. Okay, and whenever I push the hoop, it'll accelerate forward. Okay, we're going to do a few things here in this problem. The first thing we're going to do here for part A is we're going to find the moment of inertia of the hoop itself. Okay, if we set the mass of the hoop, and they were fairly light, if the mass of the hoop was something on the lines of 0.2 kilogram, that's about 200 grams, then we can turn to the back of our best friend and find the moment of inertia of a thin hoop, because this hoop doesn't have a solid center. So if we look at our best friend, or we just, you know, take a little look online real quick, we'll see that the moment of inertia of a thin hoop is, where's my pen? There we go, is equivalent to like a bunch of point masses, okay, because they're just like floating out there. We know that the center here is our pivot point, so these are kind of similar to point masses just floating around. So our moment of inertia is just equal to the mass times the radius of the object squared. So we know the mass, we know the radius, we've identified what object we have, a thin hollow hoop. So we just plug in these values. 0.2 kilograms times 0.75 meters squared. We grab a calculator real quick and we shove it all in. 0.75 squared times 0.2 gives us a moment of inertia of about 0.11, rounding, kilograms meters squared. And that's part A. That's the moment of inertia. Nothing too crazy there. It's mainly just looking at your best friend and identifying the object. Identifying that object can be a little tricky. Thin hoops are hollow hoops. Discs are solid. Solid spheres or uniform spheres are 2/5 mr squared. But hollow spheres are only 1/3 mr squared. So they have different moments of inertia depending on the type of object, what axis you're spinning around. So be careful about that. If we want to find for part B how much torque are we applying to this hoop, then we're applying this torque through the stick I'm pushing it with. Now, an important feature to remember regarding applying torques to objects is if you have a circular object you're applying a torque to, technically your force is always going to be at 90 degrees from the radial vector, or from the moment arm vector, if you like to think of it that way. The reason why is you can only apply force in a tangential velocity to the edge of a hoop, no matter which way you're turning. If you think about a yo-yo when it comes out of your hand, or if you think about, you know, a like a tube that is falling off of a rope. That rope, while it is wrapped around many times, it is ultimately going up, tangent to that hoop. So it's always going to be at 90 degrees. So whenever we use that torque equation, T equals R cross F, normally we're stuck thinking like, this is RF times the sine of some angle. But if you have a circular object and you're applying a force on the edge of a circular object, then that angle here will be 90 degrees. There's no way around that. It has to be 90 degrees there. Okay? What this means is that when we plug this 90 degrees into the sine argument, sine of 90 degrees, by the definition of the unit circle, is equal to 1. And that means what we're really doing here is we're just saying that torque equals R times F times 1, and who cares about 1, right? So all we have to do here, looking back to our picture and examining it, is say, hey, look, up here, this stick I'm pushing it with, it is sitting tangent to the circle. And my radial vector is, for my poorly drawn circle, directly out at a value of 0.75. And this angle is naturally 90 degrees. If we did our shifts as well, we'd see that. And we know the force, so we just have to say 0.75 times 12. If we take those values for the R of 0.75 meters, multiply it by a force of 12 newtons, 3/4 times 12, well, if you want to think of it that way, the 12 and the 4 are going to reduce, and in the end we are going to get a value of 9 Newton meters. That's our torque right there. So nothing too crazy for part B. Mainly identify your object. It's probably going to be circular. Those are kind of easy things for us to use. And then you're using just R cross F. In our case here, that circular object had an angle of 90 degrees. And because of that, it was just R times F. Okay. If you wanted to think about like what direction this torque is going in, if we were thinking about something along those lines, I can imagine that this is rotating this way. And with that, I'm going to get a kind of clockwise rotation.